Stanford University.
You think I don't know, don't you? No, as a matter of fact, I do know, and that's what we're going to talk about tonight, and it's called the phenomena. What is the Higgs? Higgs.
I think you started to cover this last week, and I didn't really. You described what you were talking about as giving mass to the photon, but
Yes,
of course,
that's what we're going to talk about tonight.
we don't actually give mass to the photon. So what's different?
No. That's right. That's right. The real photon, the symmetry group associated with it, is not spontaneously broken. Tonight we're going to talk about how, if the symmetry group associated with the photon were broken spontaneously, how it would give the photon a mass. Now, the reason we're doing that is because exactly that phenomena happens with the Z boson and the W bosons. The photon is a little bit simpler. Indeed, it might have had a mass. The fact that it doesn't have a mass is perhaps an accident of nature. The absence of an appropriate Higgs field. We're going to talk about what the Higgs field is to give it mass. So that's what we want to talk about tonight. How gauge bosons, like the photon, get a mass when spontaneous symmetry breaking. What is the symmetry, incidentally, when I say associated with the photon? There's a conserved quantity, which is the charge. Conserved quantities always go with symmetries. What's the symmetry that's connected with the conservation of electric charge? U1. It's the thing which multiplies the charged fields by a phase. It is a kind of rotation in the complex plane, the complex field. So I'm going to explain to you tonight how spontaneous symmetry breaking of that symmetry induces a mass for the photon. Now, there is a situation in nature where the photon does get a mass, and the symmetry of U1 symmetry is spontaneously broken. Does anybody know what it is? Well, it is condensed matter, yes. Okay, the answer is in a superconductor. In a superconductor, photons propagate with a mass. Now, that's in the superconductor. When they leave the superconductor, they're photons again. When they're in the superconductor, they behave as if they had a mass. Okay, so that's an example of the Higgs phenomena. And we can talk about it, yeah.
Would that also be the case when the photon is traveling through something other than a vacuum?
Well, the superconductivity only happens when the photon is traveling through something other than the vacuum. No, superconductivity or the photon, no, the photon does not propagate with a mass in a prism. Its velocity is slower than the speed of light, but it's still true that at zero momentum, meaning infinite wavelength, its frequency is zero. Okay, let's talk about the difference. That's an interesting difference. Might as well talk about it. The relevant issue is the shape of a certain curve. The curve is either energy versus momentum, or for waves, what corresponds to momentum for waves? Either inverse wavelength or wave number, k. Everybody remember k? K is basically the inverse of the wavelength, and vertically, what do we have instead of energy? No, k is like p. Vertical, here was energy. Frequency, omega, right? Remember, E equals h bar omega, and P equals h bar k. All right, so k is wave number, the number of waves that fit into a given, into a unit distance. All right, so these two planes are the same except for a factor of h bar. All right, what does omega versus k look like for an electromagnetic wave in empty space? Well, what's the connection between omega and k? Omega equals c times k. That's it. Omega equals c times k. Now, the same relationship, incidentally, is true of sound waves. Waves on a long string and so forth, approximately the same relationship. The difference, of course, is they have different velocities of propagation. But notice that omega is 0 when k is 0. That means on this side over here that the energy is of a quantum or wave, the energy is 0 when the momentum is 0. What do we call a particle when its energy is 0? When the energy is 0, if its mass is 0, we call it photons, yes, but we call it massless. All right, so any wave which has the property that omega goes smoothly to 0 as k goes to 0, we call massless. And typically, the shape of the curve looks like that. K can be positive or negative, corresponding to a wave going to the left or the right. Let's forget going to the left. Okay. The frequency goes to 0 when the wavelength becomes infinite. That's massless. And all that happens in a prism is that C changes. C changes. Okay. Now, what about a particle with mass? For a particle of mass, its energy is equal to the square root of p squared plus m squared. Now there's some c's there. I think there's a c to the fourth, c squared and m blah, blah, blah. C squared p squared plus m squared c to the fourth, right? But if we set c equal to 1, it's just square root of p squared plus m squared. What does that look like? That's a curve which looks like this. It's a hyperbola. In fact, if we square this, we get e squared. Let's set c squared to 1. E squared minus p squared equals m squared. That's a hyperbola. You see the difference. In this case, when p goes to 0, the energy is not 0. That's the rest mass, or just the mass, if you like. The rest mass is the value of the energy when the momentum goes to 0. All right, so two different situations. One, the velocity of light may be different in a prism than it is in empty space, but that just changes the slope of this curve and does not change the fact that the energy is 0 at the origin here. The other situation is that the energy is not 0 at the origin and has this hyperbolic shape. That's called having a mass. And notice that there's a frequency, same thing here, that a wave with infinite wavelength has a finite frequency. What does infinite wavelength mean? It means you disturb the field every place the same. You make the field absolutely homogeneous. Homogeneous means it's everywhere is the same. You shift the field everywhere and you let it go. What happens is everywhere as it starts to oscillate simultaneously, that's the phenomena over here. Infinite wavelength, 0 wave vector, the whole field oscillates. Right? Also corresponds to particles at rest oscillating because they have mass. Okay. All right, so that's what the important thing to keep in mind is that oscillations of a field, when it's homogeneous, when it has infinite wavelength, those are the things we call mass. Does that answer the question about the... yeah, okay.
So is it the wave number that changes when it's moving through a solid, is that right?
Well, you can have any wave number.
I mean, if you took a ray and run it into a piece of glass,
okay.
It's not the omega that changes.
That's right. If you have a wave of a given frequency and it shines on a piece of glass, the frequency doesn't change when it goes into the material. But as I think you're foreseeing, two different materials might have a different slope here. So at the same value of frequency, you could jump from one wave number to another, and that's what happens. Yeah.
At this situation where the entire field shifts, would that be equivalent to the concept of entanglement?
No. It's nothing to do with entanglement. This is a perfectly classical wave field phenomenon.
No, I understand that, but what I'm saying is entanglement says that this particle over here and this particle over here respond instantaneously, and by the entire field shifting, wouldn't that
No.
account for?
No. Entanglement is a situation where you have two particles in two different states which are entangled with each other. A over here, B over here, or A over here, B over here. There has to be two different states. Spin up and spin down and spin up. A classical field is when all of the particles are in the same state. So it's quite different. Yeah.
So on the curve that you drew, that looks more like the, and that one, yeah. What does that represent?
This is called, okay. The relationship between omega and k, between frequency and wave number, is called the dispersion relation. You say there's no dispersion when omega is a linear function of k. When omega is a linear, incidentally, the slope of this curve is the velocity. The omega decay is, the omega decay is the velocity of the wave, okay? So if the slope of this is constant everywhere, then all waves move with the same velocity, all right? That's light. All waves move with the same velocity. If the slope varies from place to place, for example, as it would if there was a mass, then different wavelengths propagate with different velocities. In that case, the wave will disperse. So it's called the dispersion relation. Let's name it now. Omega as a function of k, that relationship is called the dispersion relation of the wave. So the words go that a massless excitation is one with a linear dispersion relation. A massive particle is one with a dispersion relation that does not go to zero as k goes to zero, but has a curvature and a shape like that. And the mass is nothing but the energy of the quantum when the momentum is zero. So that's m. Energy of a quantum as a function of the momentum when the momentum goes to zero is the mass. All right, so that's the notion of mass, and it is connected with the curvature of the potential energy of the field at or the curvature of the potential energy at the equilibrium point, wherever the equilibrium point happens to be. Why? Because if you shift the field away from the equilibrium point, let's say everywhere, homogeneously, everywhere is the same, what happens is it starts to oscillate about there. It's pulled toward lower energy, it overshoots, goes up and goes back, and that corresponds to omega not being zero at k equals 0. K equals 0 means you shift the field everywhere simultaneously, homogeneously. All right, so we take the field and we shift it everywhere simultaneously, and the frequency at that point is the mass. If the frequency is 0, and the only way the frequency will be 0 is if the potential energy is flat as a function of the field. If the potential energy happens to be flat and you shift the field away from the minimum here, it's not a minimum anymore. It's just a flat direction. It's called a flat direction. Of all things, it's called a flat direction. If you shift the field along a flat direction, it won't respond. It'll just sit there. So that corresponds to the homogeneous field, k equals 0, having no energy, no frequency, frequency 0. All right, so you spot a massless object when there's a direction, a flat direction of the potential. Here, the flat direction of the potential is going around the rim. On the other hand, if you excite the field perpendicular to that, it oscillates. And so this kind of field has two distinct kinds of quanta associated with it, one massless, one massive. What's the massive one called in the context of the Standard Model, incidentally? Massive. It's the Higgs boson. Okay. So oscillating this way, we would call the Higgs boson, and it has a mass. What about oscillating this way? That's the Goldstone boson. It's massless, but there is no massless Goldstone boson in nature. So something happened to it. In the parlance of high-energy physics, the Goldstone boson got eaten by the gauge boson, resulting in giving the Higgs boson a mass. So that's the phenomenon that we want to do mathematically tonight. The Goldstone boson eaten by the gauge boson, resulting in a mass for the Higgs boson. Okay? Remember, the Goldstone boson is the one associated with a motion around here. The Higgs boson is the one associated with this over here. Okay, so let's go through it. There's mathematics to this. If I could do it without mathematics, I would, but I can't. So we're going to do it with mathematics. And we've already set up the ingredients. We've already set up the basic ingredients for it. All we have to do is combine them together.
So that means in the Standard Model, there's only one spontaneous symmetry breaking, and that's the Higgs field. The other
As
field-
far as it's known.
As far as
It's not a simple U1 symmetry, it's this SU2 symmetry of the weak interactions that take ups to downs and neutrinos to electrons. So it's a little more intricate than just the U1 symmetry breaking. But,
I've always, well, maybe I misheard, but I always thought I heard that the Higgs was giving mass to everything, including
including itself.
and the,
Including itself. Yeah?
is that right?
Yes? Well, no. Yes and no. Yes and no. Okay, so let me tell you what the point is. There are a collection of particles in the Standard Model which, for one mathematical reason or another, cannot have any mass unless the symmetry is spontaneously broken. Now, we're going to go through those reasons. We're going to go through them for various particles and see what the reasons are why mass is disallowed by the Standard Model without spontaneous symmetry breaking. Then when spontaneous symmetry breaking happens, all of those particles get mass, and they become the masses of the Standard Model particles. Now you might ask, what about particles that didn't require a spontaneous symmetry breaking to get a mass? Are there any particles that don't require a spontaneous symmetry breaking to get a mass? And the answer is yes, there can be. Those particles are all the particles that we don't see in the laboratory. Why would it be that we would see those which symmetry breaking gives a mass, and we don't see those that symmetry breaking doesn't give a mass? Any speculations of why that might be? Yeah. Yeah. The natural mass might be way up at the Planck scale. The natural masses of particles may be very much larger, leaving over a bunch of particles which don't have masses for what you're calling natural reasons. And those particles only get mass from spontaneous symmetry breaking. Those particles are the light ones. Those are the ones we see in the laboratory. We have every reason to believe, and in fact, I think we practically know by now, that there are additional particles in nature. For example, the dark matter particles. We don't know with absolute certainty what the dark matter particles are, but it seems very likely that the dark matter particles are particles 1,000 times heavier than a proton, for example. Why is it that those particles have large mass and the other ones don't? And the answer is, in the mathematics of the theory, those particles which have large mass don't require the phenomena of spontaneous symmetry breaking to get a mass. So we're going to go through that. that's my goal for tonight, and if we don't make it through it entirely next time, the Higgs phenomena and what the words mean. The Higgs particle gives such and such a mass. The first class of particles which cannot have a mass unless the spontaneous symmetry breaking are the analogs of the photons, the gauge bosons. So tonight I'm going to try to show you how the photon gets a mass from spontaneous symmetry breakdown, spontaneous symmetry breaking. Let's begin with a boson field phi. We did this last time, but since it's a subtle and difficult concept, let's do it again. And phi is a complex field. That means there's a phi star to go along with phi, and we can write phi in two ways. Phi real plus I phi imaginary. What does it correspond to? It corresponds to what I drew before, phi real, phi imaginary. Or we can write it as phi equals rho e to the I alpha, where rho is the distance along here. It's not a real distance in space, it's a distance in field space, and alpha is the angle. Two different ways, polar coordinates and Cartesian coordinates for the field. Now, incidentally, phi star is of course phi real minus I phi imaginary, and it's also equal, this one here, is also equal to rho e to the minus I alpha. Rho and alpha are functions of position. This is a field, so these are functions of position. And as you can see, in either case, there are two fields, the real field and the imaginary field, or the radial field and the angular field. You might begin to guess about the connection between rho alpha and the two kinds of motions that can take place here. Alpha corresponds to exciting the angular modes. If you vary alpha from place to place, it's like varying around this circle. If you vary rho, it's like moving radially back and forth. Which one do you think gets a mass? Rho. Which one doesn't get a mass? Alpha. Which one is the Higgs boson? Rho. Which one is the Goldstone boson? Alpha. Good, you got it. I hardly have to go through the mathematics now. No, really. That's what the mathematics is. Now, the trick in going through the mathematics is to write the Lagrangian for this field. It's derivative of phi star times the derivative of phi. This, of course, means time derivative squared minus space derivative squared, but I'll just write it that way. Derivative of phi with respect to space and time as four vectors dotted into each other. That's the gradient terms in the energy. And you can work them out in terms of phi and phi star. I'll tell you what they are. This becomes derivative of phi real squared plus derivative of phi imaginary squared. In other words, it just behaves as if there were two independent fields, real and imaginary. Okay. Or we can write it in terms of rho and alpha. And this would become, I'll write it down for you. You can work it out yourself. Derivative of rho squared, and then plus rho squared times the derivative of alpha squared. Rho is the magnitude of the field, alpha is the angle, but each of these are fields. And this is what Lagrangian is. You can either think of it in one way or the other, no problem. Now let's add in a potential energy. The potential energy, I'm going to assume, is symmetric. Symmetric with respect to rotations in this plane. In other words, that it really does have a U1 symmetry. For a potential energy to have a U1 symmetry, it means it's only a function of rho. Equivalently, it's only a function of phi star phi. It does not depend on the angle. So let's write that, plus V of rho. That also corresponds, well, okay, V of rho. Let's take actually, the potential always comes in with a minus sign in the Lagrangian, so let's put it in with a minus sign. A simple case would be rho squared, an energy which increases quadratically away from the origin. That's a possibility. Let's think about that possibility, rho squared. It's not really it's a possible expression. What would that correspond to in terms of phi real and phi imaginary? Just rho squared. It's phi real squared plus phi imaginary squared. That's the Pythagorean theorem. Rho squared is phi real squared plus phi imaginary squared. So if the potential was the very simple form of quadratic, we would add here phi real squared, or minus, subtract, not important, phi real squared plus phi imaginary squared. Notice the Lagrangian would actually be the sum of two terms, one for phi real and one for phi imaginary, and both of them would have a mass term. There could be a coefficient here, m squared over 2, let's say. Then you would have this situation which I drew over here, where both directions of oscillation correspond to a mass. And they're quite independent of each other. They don't even couple to each other. They don't even talk to each other. Just two separate fields, one that I labeled phi real, the other one I labeled phi imaginary. Now, there could be more complicated things here which would couple them together, but this is the basic picture if the potential looks like this. But what if the potential looks like this? That's also a function of rho, but it would be inconvenient to represent it in terms of phi real and phi imaginary, especially since the minimum is stuck out here away from the origin. The coordinates phi real and phi imaginary are not obviously the best coordinates when you're stuck out here. Better coordinates are the angular coordinate and the radial coordinate. Why? Because they correspond to two different kinds of oscillations with two different frequencies. In other words, just think of this as a function of rho and alpha. Now, this potential energy doesn't depend on alpha at all, okay? But it does depend on rho. It depends on rho in a way which is minimized when rho is equal to F. And in fact, it takes a good deal of energy to displace it away from F. So it's natural to write that rho, it's natural to write that rho is equal to F plus a bit of fluctuation. In other words, the minimum energy is when rho is stuck at F. Anywheres along here, rho is stuck at F. But you can displace it a little bit, and let's represent that displacement away from F by a letter of the alphabet. And I'm going to choose the next letter of the alphabet after F, which is H. H for what? H for Higgs. Okay? H for Higgs. All right? So the Higgs field is just the displacement of the radial direction, or the radial part of the field, away from its equilibrium. All right, now, it cost a good deal of energy to excite this Higgs field. Why? Because it's got a potential, and that potential might be rather sharp. In fact, it is rather sharp. So to some approximation, some rather good approximation, we might say that the low energy behavior is as if rho were frozen at value F. Now, this is a very common thing in physics to say that there are low energy excitations, low energy oscillations of a system, low frequency oscillations, and high frequency oscillations, and ignore the high frequency oscillations. That would be equivalent to ignoring H here. Just saying rho is equal to F plus something that takes too much energy for us to worry about today. We'll worry about it another day when our accelerators have more energy. Okay? What would this look like then? Well, rho is stuck at F. We might as well ignore its derivative. Okay? Furthermore, what about V of rho? V of rho is just V of F. So V is stuck at the minimum, If it's stuck at the minimum, it doesn't vary from place to place. This and this are irrelevant to the dynamics of the angular field. Furthermore, since it costs so much energy to make a bit of h, we can just approximately say that rho is equal to F, and we find that for the low energies, for the small energy excitations, that the Lagrangian is just F squared, a number, times the derivative of alpha squared. There is no potential energy associated with alpha. Why is there no potential energy associated with alpha? For the obvious reason that we don't gain any potential energy when we go around the angular direction. All right. This is a little bit less familiar because it has this F in it, but we could redefine the field. We could redefine the field by inventing a new field, call it beta. Beta is equal to F times alpha. It's just a rescaling of the field. Just a redefinition, and then we would rewrite this as just d beta squared. No mass term. No mass term because it doesn't cost any energy to displace the field homogeneously everywhere. Right? No mass term, and so alpha or beta, depending on which you want to write, is a massless field. It is the Goldstone boson. And as I said, what its energy corresponds to is slow variations of the field. As you vary the field from place to place, slowly, you get a little bit of energy. If you vary it slowly enough, you get a little bit of energy from the derivative terms here, but no potential energy. So that's the hallmark of a massless particle, and it's the Goldstone boson. Goldstone bosons are the massless particles which are the consequences of the spontaneous symmetry breaking of a continuous symmetry. Okay, that's the buzzwords. Now, that's half the story. That's the spontaneous symmetry breaking half together with the Goldstone boson phenomenon. The other half of the story, which also has to do with varying the phase of a field from point to point, is the gauge invariance. So I want to spend a little bit of time. I'm going to give you a break for a few minutes. Then we're going to review again what I told you last time about gauge invariance. That should take us another 15, 20 minutes, or 10 minutes, I'm not sure. And then put the two of them together and see what comes out. Okay? And what will come out will be that the Goldstone boson is eaten by the gauge boson, giving the Higgs boson a mass. No, giving the Higgs boson a mass and also giving the gauge boson a mass. Yeah.
I'm confused whether rho is the radius in the complex plane or is the field value at a radius in the complex plane.
No, it's the field is a point in the complex plane. The value that a field takes on is a point in the complex plane. At every point in space, the field has a value which is a complex point in the plane. In other words, at one point in space, the field is 3 plus I times 6. At another point in the plane, it's pi plus I times E. Someplace else, it's the Euler-Macaroni number plus I times the Shmulevitz number.
We haven't specified where in the complex plane that is, except we've said that it's radially symmetric. Except we've said that it's radially symmetric.
What's radially symmetric?
The value of the field at any...
No, the value of the field at a point is not radially symmetric. The value of the field at a point is the value of the field at a point. It's not radially symmetric, it's the point on the complex plane. What's radially symmetric is the potential energy. The potential energy is only a function of this squared plus this squared. 3, 6, the field at some point has the value over there. At some other point in space, the field takes on the value over here. At some other point, it takes on the value over here. The potential energy is only a function of the sums of the squares of these.
But 3 plus I6 is the value of the field, and it doesn't say anything about where in the complex plane that occurs.
3, 6.
value of the field at x plus iy is.
No, it's not the value of the field at x plus iy. The value of the field is x and y are not positions of space. This is not the field at the point x and y. This is the field whose value is a point in the complex plane. It's an abstract idea. Fields can be complex, they can be real, they can be multi-component. You can assemble them together if they have two components into a complex variable. So the field itself is a complex variable. It's a complex variable where as you move around in space, the field takes on different values on this complex plane. Get used to that idea. Fields don't just have to be numbers, they can be complex numbers, they can be multi-component objects. Yeah.
Question. In the sombrero picture there, going in the mass fold direction, if you give it a big enough displacement, it'll go into the other equilibrium point.
Yeah.
What does that mean in terms of...
Give it a hard enough kick, it'll go over the top. It'll swing around.
Does that manifest itself in some constant particle? Or?
Well, the problem is that the amount of energy that would be involved for the Higgs field is way beyond the energy that even a big accelerator can. So it's out of the ballpark from even the LHC. But yes, I mean, in principle, you could give the field a big enough knock to knock it over the top. Not everywhere simultaneously in space. That would be an enormous amount of energy, but in some region, yeah.
But if that were exactly in line with the peak of the thing,
Very
then it
unlikely.
would go off and wind up all over.
Right. So it's very unlikely. Right. That's right. Yeah, it would make a monstrous splash of some kind going off and on. Let's take a 10-minute break. Okay. Let's go through again what we mean by a field as a function of space and what this idea of a field which is a complex variable is, just to make it clear once more. We have space, x, y, and z, right? All right. Now we can have fields in space. Let's say scalar fields. You can have a scalar field in space, now what characterizes it as being a scalar? It means it doesn't change when you rotate coordinates. That's all it means. It doesn't change, not when you rotate the coordinates we're talking about here. When you rotate the coordinates of real space, it doesn't change. That's what a scalar field is. Now you can have several scalar fields. Let's say in particular you can have two scalar fields. Let's give them names. Let's call them phi I and phi r. They're two scalar fields. You can then assemble them if you like. This is totally a matter of convention. It's totally a choice. It's a useful choice. It's one of these things in mathematics which sometimes are really just useful conventions, and this is one of them. In fact, the whole idea of complex numbers is a useful convention. It's a useful convention for representing pairs of numbers, that's all. And the pairs of numbers are called the real and imaginary parts of the numbers. Better not call them x. X stands for space, okay? But just real and imaginary components are just ways of speaking about pairs of real numbers. Now, it is a little more than pairs of real numbers. There's more structure that goes into the complex numbers, but fundamentally, it's a way of talking about pairs of numbers. You can plot pairs of numbers on the Cartesian plane. The Cartesian plane is not real space. It's just the Cartesian plane on which you've plotted the real and imaginary parts of complex numbers. If I had two fields, two scalar fields, one of which I called phi real, and the other, that's its name, phi real and phi imaginary, I can assemble them together into a complex field. Okay? Yeah, a complex field. And at each point of space, there would be a phi real and a phi imaginary. Okay? At each point of space, I could go and plot the value of the field on the complex plane. Keep in mind, the complex plane is not space. It's just an auxiliary construction An auxiliary construction which is useful in replacing two real fields by one complex symbol. That's all it is. It's a trick for representing, for cutting down the number of equations that you write. Cutting it in half, basically, by writing them as equations for complex variables. Okay, so in that language, you would say that the scalar field, the complex scalar field phi, is that just that? It's a complex scalar field, and at every point in space, real space, it has a value. That value is not a single number, it's a pair of numbers. Why? Because it's a pair of fields to begin with. That pair of numbers can be plotted. So at this point of space over here, the field is over here. At that point of space, the field is over here. At that point, it's over here, and so forth. That's the idea of a complex scalar field. Sometimes the real and imaginary parts are called the real and imaginary components of the field, but don't get those confused with the components of a vector field or a tensor field or the components of the gravitational field. Those components have to do with projections onto real space-time coordinates. This has to do with the projections onto this fictitious two-dimensional plane that's useful for writing pairs of numbers. Now, once you realize that you can write the field as a complex variable and plot it on the two-dimensional plane like that, then it becomes a possible symmetry of nature or a possible symmetry of mathematics to rotate the field. In other words, there might be a symmetry which says that you can relabel or redefine phi I and phi r by rotation, and that happens when we have Lagrangians like this, which don't change when you do what? When you multiply phi by e to the I times a phase. These are the class of Lagrangians which don't change when you rotate the field simultaneously everywhere in space. When you rotate it in this fictitious plane. In other words, you take the field at every point of space and you rotate its value. You give a new value to the field, which is related to the old by changing the angle here, rigidly everywhere in space. Then this Lagrangian does not change. We went through that last time, and that's the basic idea of a complex field with a symmetry of, it's called U1 symmetry. It's a global symmetry? It's a global symmetry. That's called a global symmetry. A global symmetry is one where you're not allowed to change the phase angle in space. You just rotate it everywhere. Yeah.
So you can see that symmetry just by looking at what's a function of rho?
Yeah. Well, you can look at it in a number of ways. You can see that since this has real squared plus imaginary squared things in it, whenever a thing is a function of real squared plus imaginary.
And the other term was?
This one?
And the other term was the Pythagorean theorem.
Yeah.
Right.
Right. So this is a function of rho also. You can see it here. Incidentally, what does the symmetry operation do on rho and alpha? Rho stays the same. And alpha? You shift it by a constant, namely the angle that you're rotating the field by. Well, shifting alpha by a constant doesn't change its derivatives.
Yeah, that's why I was saying that the potential is the only part where
Right.
the derivative doesn't come in.
That's correct. Right. So, all right, now I think we have the basic idea. Now let's go through again. All right, now, yes, let's go through the idea of a gauge transformation. We went through it last time, so I'm just going to remind you. We're not going to spend a lot of time on it. We're going to do it as fast as we can, but please ask questions. It is not a symmetry of this Lagrangian to multiply the field phi by an arbitrary function of position, by an arbitrary phase. This is called a phase, e to the I times this times phi of x. This is not a symmetry. We went through this last time. We rewrote that Lagrangian in terms of phi prime and found out that it didn't have the same form. In other words, the Lagrangian written up there, in particular, the term derivative of phi star times the derivative of phi, I don't have to put in the indices mu here, you know about that. That is not the same as the derivative of phi prime star, derivative of phi prime. Not the same, and therefore it is not a symmetry. Okay, this is not a symmetry. Why? That's because when the derivatives act, they act not only on phi, but they act on theta here. They act on theta if theta is variable. If theta didn't vary in space, then this would be a symmetry. But if theta varies in space, it's not. We worked that out in detail last time, and I'll show you in a moment what we found. But to make it a symmetry, you have to add another field, a kind of compensating field. A compensating field that will compensate for the changes in the Lagrangian when you shift the phase of the field. Keep in mind, it's useful to remember that shifting the phase of the field is just adding a function to alpha. Okay? Shifting the phase of the field is adding a function phi of x, theta of x to alpha. It changes the phase angle everywhere by amount theta. All right? If theta is a constant, it's a symmetry. If theta is not a constant, it's not a symmetry. In order to make it a symmetry, you have to add another field. And the other field is called the vector potential. Right? It's a 4 vector. It has an index mu. It's also a function of position. Out of it, you build the electromagnetic field, E and B, your electric and magnetic field. The transformation property, when you do a gauge transformation, like this is called a gauge transformation. When you do a gauge transformation, you have to do something to A at the same time. In fact, you have to take A prime of x and set it equal to A of x plus or minus. I always get confused by the signs here. I think it's plus the derivative, this is A mu of theta. In other words, you add to A the gradient, the space-time gradient of theta. If you do these two operations together and you construct the right kind of Lagrangian, it will be invariant under this operation. If it's invariant, it's a symmetry. So let me remind you how it works. Oh, incidentally, oh, that's good enough. That's good enough.
This time you have a minus there. You had the minus there last time.
Yeah,
Oh, last time I had minus?
I think the idea is that A goes to A prime plus d mu.
Theta, d mu is theta.
I'm just saying if you write it with an arrow notation of the transformation going from starting with A mu
Yeah.
and going to what, then you have a minus sign. If you write the transformation as A mu goes to A mu plus d mu, okay, then when you write it in the A prime,
Okay, yeah, it's just reading it the other way.
then you have a minus.
Yeah, right. All right, but this is the transformation that you make. These are the primed variables, these are the unprimed, and I may have written it the opposite way last time. I don't remember, but I will compensate for any mistakes, not any mistakes, but any change of notation by changing it consistently everywhere. From one week to another, I don't remember the precise notation, but both of them, you can do it either way.
You wrote that D equals del plus IA and D star equals del minus IA.
I may have inadvertently changed notation. But as long as you do it consistently everywhere, it's fine. Okay. So let's now, we've seen that the ordinary derivative of phi prime is not simply related to the ordinary derivative of phi. Let's write out the relationship. Let's take the derivative of phi prime. derivative with respect to any axis. I'll stop writing mu's and nu's. The derivative of phi prime is first of all equal to e to the I theta, which is a function of x times the derivative of phi. If that's all there was, and we did multiply the derivative of the complex conjugate of phi by the derivative of phi, the e to the I thetas would cancel out, right? All right, so if that's all there was, we'd be in fine shape. We would say there's a symmetry. But there's another term, and the other term is phi times the derivative I times the derivative of theta, all times also e to the I theta. It's this term here which is the nuisance. If all there was something which carried if theta only entered through e to the I theta here, it would cancel out when we multiplied this by the complex conjugate. But theta comes into its derivative over here. That's the problem. Okay? All right, to fix that problem, why should you want to fix it? Well, it's a fact of nature that there are gauge symmetries. That's also an interesting fact of mathematics, that such symmetries are possible. To make it possible, you replace the ordinary derivative by what's called the covariant derivative. This is a mathematical concept that comes from the theory of fiber bundles, but I don't know whether the theory of fiber bundles was invented before or after the notion of gauge invariance in physics. I have a feeling it was invented afterwards, but somewhat independently.
Gauge invariance was really vile when he tried to
Right.
get relativity electricity.
That's right. I think so, yeah. Right. I don't know, but I don't know whether mathematicians invented it completely independently through the, but I really don't know. In any case, it is both a mathematical and a physical concept. And in order to make the Lagrangian gauge invariant, you invent a new kind of derivative. Right? It's called the covariant derivative. With respect to each direction of space or time, you write that this is equal to the ordinary derivative I think it's plus. Now I'm going to get myself confused. I'll try plus. If it doesn't work, we'll change it. Plus I times A times phi. Now, there is an implicit index in here. Once more, I will write it. Just remember, A is a vector. Derivative plus multiplying by A. Sometimes this is indicated by saying that derivative is replaced by derivative plus IA. But it only makes sense if you apply it to a complex field like phi. Right? So this is the definition of the covariant derivative. And if I were to write the covariant derivative of phi star, it is by definition just a complex conjugate. So it's equal to d mu phi star minus I a mu phi star. Okay. Now I assert, easy to check, that the relationship between the covariant derivative of phi and the covariant derivative of phi prime is very simple. All you have to do is evaluate the covariant derivative of this is the covariant derivative of phi. Let's write down what the covariant derivative of phi prime is. Well, it's exactly the same, except you stick primes everywhere. D mu phi prime is just equal to d mu phi plus I a prime times phi. Phi prime, thank you. Phi prime everywhere. It's phi prime. Phi prime. Okay, if you stick phi prime over here, you're going to wind up with this extra term over here. As if I evaluate d mu phi prime, let me write it better. D mu phi prime. Here it is. Let's see, is this right? No. What did I do here? This was d mu phi prime, right? Phi, they're all phi. No. Yeah, no, there's no difference between capital and not capital. No, there isn't.
So regular phis are actually lowercase, and when you use the bars, they are uppercase.
Sorry?
When you don't use the bars, they're lowercase.
What bars?
His phis are case.
What bars?
If you don't have the I bars on the top and the bottom, phi is lowercase.
Sorry, where's I bar?
You know, those bars that you write on the
These?
top? Yeah, like those things.
It's uppercase phi.
Yeah, that's an uppercase.
Yeah, I'm just telling you, there's no distinction in my notation between uppercase and lowercase. Sometimes I like to put those little things there when I'm feeling in a good mood, I put these things on. When I'm not feeling in a good mood, I leave them out.
I see. So
That's it.
in most of the books, they use lowercase,
Yeah.
but then for special cases, they will.
No. Okay, phi is phi. Phi is phi, and I have not I did not mean to distinguish uppercase from lowercase. Wait. I got to put in all, just a minute, I want to be consistent here.
What would either erase the other two?
What?
What would either erase the other two?
Erase where?
That's just kidding.
Oh, okay. Now, was there a question?
He was asking about indices balancing upper and lower.
I don't remember my special tip, my four vector. Do we need an index up and index down convention on the derivative?
Yeah. What's really meant by d mu phi star d mu?
Is one a conjugate? Is one the complement conjugate of the other?
No. They are the, okay, so if you have a four vector, an arbitrary four vector, v mu, you can multiply it by g mu nu, that's the metric, and get v mu, v nu. All right, the meaning of this symbol for ordinary special relativity is that the time components of these two are the same in sign, and the space components are opposite. All right, so, right. The meaning of this is it should be taken to be the covariant vector times the, right. But I don't want to write that every time over and over, so I just write an abstract symbol derivative times derivative. Yeah.
I think you have to have the lowering operator there. You have lower on the left, upper on the right.
Sorry, you're right. Right, thank you. Right. But we've already gone through special relativity a number of times, and so I don't feel the need to be so careful about relativity indices. Right, so I won't even bother writing them for the most part. I keep saying I'm not going to write them, and I keep writing them. Okay, good. Now, here, right. If I plug in d mu phi prime, I will get this unwanted, nasty piece over here. But if I also plug in a prime times phi, where is a prime? Let me write a prime over here. A prime equals a, it's either plus or minus d mu theta. Then they will cancel. They will cancel. There will be a term I d mu theta times phi. You know what I mean? Right. So if the two d mu thetas will cancel each other. One from calculating the derivative here, and the other from the explicit difference between a prime and a. So what will I find? Well, I'll tell you exactly what I will find. I will find that d mu phi prime, this one over here, is equal not quite to just d mu phi. What am I missing? E to the I theta. Overall, e to the I theta. So you say, well, I didn't get anywheres. D mu of phi prime is not the same as d mu phi. It's not gauge invariant. True enough, but it only differs from being gauge invariant by an outside overall factor of e to the I theta, which will disappear when you multiply this by its conjugate. Okay. Notice that in this formula here, the derivative of theta does not appear. You have the covariant derivative of phi prime is equal to the covariant derivative of phi up to this overall factor of e to the I theta, which will cancel when you multiply this by d mu of phi star prime. That will be equal to e to the minus I theta times d mu of phi star. So when you multiply these two together, the unwanted, unpleasant things that have derivatives of theta in them disappear. What is the cost? The cost is you had to introduce a new field which transformed in this way, in this way over here. But once you allow yourself that freedom to introduce a new field, the vector potential, then this Lagrangian over here becomes invariant under gauge transformations. Later on, we'll write it out in some more detail. But one more point before we jump to the conclusion, and that's the electromagnetic part of the Lagrangian. This field is a charge-carrying field. It's not the electron because the electron is not a boson, but it could be some charged boson of some sort. Okay? Some charged boson of some sort, and there are charged bosons. A helium atom is a helium nucleus is a charged boson. So phi represents some charged boson. A represents the vector potential, and the electromagnetic field is also governed by a Lagrangian. The Lagrangian is defined F mu nu to equal d mu a nu minus d nu a mu. The space-time, the mixed space-time component is the electric field. The space-space component are the magnetic fields. And the square of F, now that there are some signs that go into it, F mu nu, that's E squared minus B squared. That's the Lagrangian of the electromagnetic field. The important thing for us is that this is gauge invariant. This does not change when you make a gauge transformation. What happens to A? A changes by the gradient of theta. So what happens to this? F prime becomes F plus d nu theta minus d mu theta. These two terms cancel. So F is itself gauge invariant, and when you add F squared, it's still gauge invariant. So the whole upshot is, oh, one more thing you can add that's gauge invariant, and that's a potential which depends only on phi star phi. A potential which depends only on phi star phi. So the full Lagrangian of a simple gauge theory involving the interaction of electromagnetism with a charged scalar field would look like this. It would have d mu phi, d mu, let's just put d phi star. It would have v of phi star phi, which is just v of rho if you remember, and then plus f squared, plus e squared minus b squared. And it would be fully gauge invariant, no change in it when you make a gauge transformation. That's the simplest gauge theory in a nutshell. And that's basically it. That's basically the structure of all gauge theories. They have a structure similar to this. Now let's ask, what happens when the symmetry of rotation of phi is spontaneously broken? When does that happen? It happens when the potential has this upside down sombrero, I guess it's not an upside down sombrero, when it has that shape so that the ground state of phi breaks the symmetry, what happens? What new thing happens? So what new thing happens? Oh, before we do that, let's just remember that this potential is such that the angular direction is a Goldstone boson, no mass. The radial direction, which we call the Higgs boson, has a mass. And furthermore, the photon does not have a mass. How do I know the photon doesn't have a mass? The reason is simple. The F is only a function of the derivatives of the vector potential. That means if you were to shift the vector potential everywhere simultaneously, there would be no change in energy. Okay? Shift the vector potential everywhere together, no change in energy. That means a massless particle. So there are two apparent massless particles floating around in this theory. One is the Goldstone boson, and the other is the photon. And now, watch what happens. Let's take. Oh, what would a mass term for the photon look like if you had one? Well, the mass term is always something which is quadratic in the field. For example, the mass of phi, if it existed, would be phi star phi, or phi squared, phi real squared plus phi imaginary squared. What would the photon mass be? It would be something proportional to a squared, to the vector potential squared. If you allowed yourself to put the vector potential squared into the Lagrangian, you would have a mass for the photon. That would not be gauge invariant. Look at it. Here's a squared, which means, this means a mu, a mu. If you put that into the Lagrangian, what would happen when you make a gauge transformation? It would shift to a plus the gradient of theta squared. All right? But that's not the same as a squared. A squared is not the same as a plus derivative of theta squared. So a squared, just a squared. A squared would not be gauge invariant. So a mass term is not allowed by gauge invariance. Gauge invariance is a symmetry which prohibits the photon from having a mass. Or does it? Well, let's look at this Lagrangian a little more closely. And in particular, let's look at this term over here. In fact, let's concentrate on the Goldstone boson piece of it. And we can do that by writing that phi is F times e to the I. No, let's not. Let's go for it. Here's the term in the Lagrangian. All right, so what's in here? D phi is derivative of phi plus, is it plus I a times phi? Is that right?
Could be. It's what you wrote.
That's what I wrote. D phi star is derivative of phi minus I a phi star, right? Now let's suppose that we're looking at the ground state when the field is right over here, when phi is equal to F. Let's say just the real value. The real value of phi is equal to F. For simplicity, let's say the imaginary part of phi is 0. So the field is sitting right over here. Let's look at the various terms. First of all, well, the most important term is this one here, a times phi star. But phi times phi star is stuck at the minimum here. It's stuck at the minimum because it takes a lot of energy to shift phi away from the minimum. So, as long as we don't excite a lot of energy, there's an effective term in the Lagrangian, which is just a squared times phi star phi, which is just equal to f squared times a squared. Right? Somebody said, Why'd you say, Because you immediately see that this is behaving like a mass term for the photon. This is behaving exactly like a mass term for the photon. What's the mass? The mass is basically just F, actually twice F, well, square root of 2 times F. But this factor, this numerical factor here, is playing the role, forget this, it's playing the role of A squared times F squared, which would be a mass for the photon. It would be an energy that you get when you shift the field homogeneously. Okay? So, what have we learned? We've learned that when you spontaneously break the symmetry, when you study the theory in the neighborhood of the minimum over here, the effect of one of the terms in the Lagrangian is just to make a mass for the photon. Isn't that interesting? When the photon propagates in this world where the symmetry is spontaneously broken, it behaves as if it had a mass. And it does have a mass for all practical purposes. So we've gotten around the statement that says photons can't have mass. Now, real photons, of course, don't have mass. But these photons in this world with a spontaneously broken symmetry do have mass. The second thing is the Goldstone boson disappears. Why does the Goldstone boson disappear? Well, let's remember what the Goldstone boson is. It's this angle alpha, the angle of the field on the complex plane. What does a gauge transformation? Well, first of all, what is the Goldstone boson? The Goldstone boson is simply a slowly varying or a varying value of alpha. Alpha is a field. It can vary in space. If it couldn't vary in space, it wouldn't be interesting. Alpha can vary in space. But you can make alpha vary another way. You can make it vary by doing a gauge transformation, adding a little bit of theta of x. So you can make alpha vary from place to place, and you might think that that makes a Goldstone boson. But it doesn't, because this is a symmetry. A symmetry means that you don't change the energy. It means that the system stays in the ground state. This is not a real change. It's a gauge transformation. So the Goldstone boson completely disappears. It completely disappears. It just becomes a gauge transformation, no real energy associated with it, and at the same time, the vector potential gains a mass. So it's a sort of zero-sum game. You get rid of one mass. Well, no, it's not a zero-sum game. You've removed the massless Goldstone boson and removed the massless photon, replacing the massless photon by a massive photon. And at the same time, the Higgs boson now has a mass because it oscillates about here. That's the Higgs phenomenon. It, by plugging in, basically just by plugging in the value of the Higgs field, or the value of phi, at the minimum here, we generated a mass term for the photon. And where did it come from? It came from this covariant derivative. That's all. It just came from the covariant derivative.
Could you rewrite the whole Lagrangian in
What's
those?
that?
Could you rewrite the whole Lagrangian in those terms?
Yes, you can. And yes, you can. You can rewrite the Lagrangian in those terms. You can do a gauge transformation and basically completely remove this angular degree of freedom. Completely remove the angle from the... I'll show you a simple baby version of that. If you completely forgot the radial degree of freedom, just completely froze it, you would find that the Lagrangian, let's see, the covariant derivative of phi would become f, I think, times the derivative of alpha plus the vector potential itself, maybe times e to the let's see, phi is just equal to f times e to the I alpha, and so the derivative of phi is f I alpha, sorry, f if derivative of alpha times e to the I alpha. So there would be an e to the I alpha multiplying the whole thing. This is just setting the magnitude, or the rho equal to f. Okay. I think f would come on the outside here, wouldn't it? F would come on the outside. This would be the covariant derivative of phi, and it would contain the derivative of the angular part. That's the important thing. It contains the derivative of the angular part. Right? What about the derivative of phi star? That would be the same thing. Derivative of alpha, I here, minus IA times e to the minus I alpha f. I'm getting tired, so it's getting a little bit late. That's what you would get. Okay? When you multiply them together, you would get exactly what you expect. Okay, now you also have f mu nu. You have this times this in Lagrangian, and you have f mu nu squared. Now let's make a gauge transformation. This is a clever gauge transformation which is designed to get rid of this term altogether. How can you make a gauge transformation that gets rid of this term? Just set theta equal to minus alpha. Remember what happens to the vector potential when you make a gauge transformation. It just picks up a derivative of theta. If you make your gauge transformation using, for the gauge function theta, alpha itself, this just goes away completely. Or, sorry, it doesn't go away completely. It just becomes a. Right? And this term in the Lagrangian just becomes a squared. So by design, you can construct a gauge transformation which just removes this. This times this gets rid of the alpha dependence altogether, and you just get f squared times a squared. All you get is the mass term. That's all that's left. And of course, you still have f squared, but this is gauge invariant, so it doesn't change when you do the gauge transformation. Net result, the angular degree of freedom just sort of disappears. Some magic happened, the angular degree of freedom disappeared, the Goldstone boson is gone, and the photon has a mass. Meanwhile, the Higgs boson, which is this radial oscillation, that's still there. Okay? So this is the magic of the Higgs phenomena, and it's the phenomenon of giving a mass to the gauge bosons by spontaneous symmetry breaking.
Is it fair to say that the oscillations in alpha are indistinguishable from just gauge oscillations?
From just gauge trend. Yes, that's fair to say. It's not only fair to say, it's true. Now, I will tell you right now that this is also the physics of superconductors. In a superconductor, there are charged bosons. The charged bosons are bound pairs of electrons. They're called Cooper pairs. Cooper pairs are loosely bound pairs of electrons, but they are bosons. Okay? So there's a charged boson field in the system, and the charged boson field gets shifted away from the origin by some complicated dynamics in the superconductor. It creates a condensate of those charged pairs, and it's equivalent to exactly this kind of spontaneous symmetry breaking, where phi would be replaced by the field describing the Cooper pairs. So this is also the physics of a superconductor, and in the superconductor, the photon also behaves like a massive particle. One last thing. How can you lose the degree of freedom? How on earth can the degree of freedom disappear, the angular degree of freedom? It didn't disappear. What has happened, a massless photon has two polarization states. Remember, a polarization is a little arrow that is perpendicular to the motion of the photon. It's, if you like, the direction of the electric field oscillations. So every photon carries with it a polarization vector. There are two orthogonal directions for the polarization. If the photon is going that way, the polarization can be that way or it can be that way. So there are two polarization states. You can also think of them as the states of circular polarization of the photon. There is no state in which the polarization vector of the photon points along the direction of motion. Maxwell theory doesn't allow that. Why is that consistent if the photon is described as a vector? How can it be that it only has two components and not a third? And the answer is very simple. The photon moves with the speed of light. It can never be brought to rest. Suppose it could be brought to rest. Supposing the photon could be brought to rest. If it could be brought to rest, and you brought it to rest, it was going down that way, and you brought it to rest, it had a polarization along the x-axis, and you brought it to rest. It would be a particle at rest with a polarization along the x-axis. Right? Now you could accelerate it along the x-axis, and all of a sudden it would become a particle whose polarization was along its direction of motion. So the answer is, if a particle like the photon were to have mass, it would have to have three directions of polarization. You could bring it to rest, and once it's at rest, there's no distinction between the three directions. It would have to have three directions of polarization, and then if you sped it up along some axis, it would have three directions of polarization. The massless particle can never be brought to rest, and it's perfectly consistent for it to only have two directions of polarization, namely circular this way or circular this way. Another way of thinking about it is if you take a particle circularly right-handed polarized, and you brought it to rest and then accelerated it off in the opposite direction, it would all of a sudden have left-handed polarization. It would have left hand, so, all right, it's also a way to think about it. The point is that you have not lost a degree of freedom. The Goldstone boson has really become the other missing polarization of the photon. Or another way of saying it is you started with 4 degrees of freedom, the two components for each photon, the two components of the charged scalar and the two components of polarization of the photon. In the end, you were left again with 4 degrees of freedom, 3 polarizations of the photon and the Higgs boson. So you really haven't lost any degrees of freedom. You've turned the Goldstone boson into what's called the longitudinal degree of freedom of the photon, the one in which the vector potential or the field is pointing, the electric field is pointing along the direction of motion. That's what's happened. But they all have mass. Now the next time I will show you the physics in a simplified context, the same context, of why the fermions, the electrons, and the quarks get their mass from the Higgs phenomenon. So far we haven't talked about the quarks and the electrons. They also have mass. What does their mass have to do with the Higgs phenomenon? That will be the next time. When we finish that, we will have a setup in which all particles, including the Higgs boson, all get their mass from the same place, namely the spontaneous symmetry breaking. Then we can start to talk about this very interesting situation that all of the particles in nature that we know, that we've measured, are the ones which would become massless if there was no spontaneous symmetry breaking. Boy, I've had enough for tonight.
For more, please visit us at stanford.edu.